So the last talk of the day is by very old fellow, Ana-Andreea Stoica, who's going to talk about diversity and inequality in information diffusion on social networks.
Yeah, thanks everyone for sticking around and for not leaving the talk to go get cupcakes upstairs. But okay, so let's get started. This talk is very related to some of the talks we've seen today, and it has a flavor of thinking more about the communities that are involved in information diffusion. So I've done this work at Columbia where I was a PhD student with my advisor, Augustin Chantreau, and one of our collaborators, Jessie Shinihan, who's also now a PhD student. And for a brief introduction, although we've seen a lot of that today, information that's propagated through a social network has ramification in a bunch of applications, from the news that we read, technologies we hear about. We know that the problem of information diffusion, as Mohammed pointed out, started from running marketing promotions in an efficient way, and it has bigger ramifications than that, such as public health issues, who gets access to vaccine, who hears about them, and so on. And depending on what application we're using, the setup of the problem may look very differently. In running marketing promotions, at least in the current ones, we think more about having a small and targeted campaign that reaches a subset of the population for which we think the information is relevant. Whereas in a public health issue case, we would think about a central planner that's trying to distribute information to as many people as possible in a way that's efficient. And that requires a much larger campaign. And this is the kind of applications that we care about, and we want to think about who are the people who this information reaches and what groups are they part of. As a motivating example, as we spoke about COVID and access to vaccine, there's been a lot of research in showing that there is a gap in vaccination between more and less vulnerable groups in the US, particularly depending on different counties, but also correlated with race. And in particular, Hispanics have one of the lowest vaccination rate. This is an example from New Mexico from last year, compared to the general population. And many people have thought, well, maybe that's vaccine hesitancy, but that's not the entire explanation. And other recent surveys were showing that they are some of the most willing groups to receive COVID shots, but it's about having access to information about the cost and access, and having access to correct information about it. So that's where the problem lies on, like, how do we fix this gap in information access between groups? In this case, when we may think about demographic groups in these applications, we may think about different types of groups in general. And beyond the access to public health guidelines and issues, there are a bunch of other applications like opportunities. Like Mohammed talked about the diffusion of microfinancing loans among people in rural villages in India. And again, like, how do you make sure that you diffuse information among these groups and think about the network structure that's particular to these groups as opposed to more urban settings? So with that in mind, I want to get to how we define this problem and how we formalize it. It's been formalized as a very classic problem by Kempe, Kleinberg, Tadorsh in 2003, and we've seen this formulation before. For everyone who hasn't seen it earlier this day, the main idea is that you have a network of people and you're trying to diffuse. You have a central planner who's trying to get a piece of information to as many people as possible. And you can't get it to people directly. So what you do is that you want to have a selection of an early adopter set, a set of people who first receive this information, and rely on them to spread it to their friends, who spread it to their friends, and so on, in a process that cascades. So how do you select these people based on a particular budget that may depend on your constraints, computational costs, and so on, is the actual optimization problem. So phi here might be the diffusion function, S is the selection of this early adopter set, and K is your budget. And there are many models to think about how you diffuse information. In this case, we're thinking about the independent cascade, where everyone diffuses information with a probability P independent of everyone else. This is the model that Mohammed used in his talk about information diffusion as well. So as we know, this problem is NP-complete. We can't solve it directly, but we have some approximation algorithms that are able to think about it and to approximate a good solution for the selection of this seed set or early adopters. And those rely on centrality. We've seen algorithms that think about degree, people who are very popular, Sometimes they do good, sometimes they don't do that well, distance centrality and eigenvector centrality and so on. And other algorithms that think about doing this in an iterative way like greedy, which does have theoretical guarantees for how close it can get to the optimal solution, but it's very computationally expensive. And as Mohammed mentioned, it requires full network information, which sometimes is really hard to get. Beyond this, what all of these also have or don't have in common is that they're agnostic to communities. They don't take directly into account different communities that may be present in our network, like demographics and so on. And because of that, people have shown that very recent work has shown that if you don't take into account community affiliation, you might reproduce bias, which is present at the level of centralities in the outreach as well, which may mean that groups, certain groups, particular minority groups, may be left out of the information loop in the outreach. And there's a gap in access in who gets this information that you're trying to spread. And here I'm portraying blue and red, which can represent demographics, gender, interest groups, depending on the application that you mostly care about. So this work showed this both empirically and theoretically from 2019. And we were thinking at the same time, when we're publishing our work on like, how do you fix this problem? And the way this work from Ben Fish et al. Was thinking about it was to say, well, I want to recover that gap in information access between the two groups. So I can impose a constraint in my optimization function at the level of the outreach. So I want the proportion of people who have heard this information, who are from one group and the other group, to be more or less the same as my proportion of groups in general. If I have 30% of people who are red, I want 30% of people who have heard this information to be red or to have this red label. And they have shown that when you do that, well, you might end up with this fairness efficiency trade-off, which is prevalent in many problems when you think about fairness in this particular way. And the way this trade-off looks like is that if you don't impose any constraint on your problem and you just want to use some centrality metric to optimize for maximizing the outreach, maybe you're going to reach a lot of people, but maybe one of the group is going to be severely underrepresented. Meaning that, let's say if you have equal numbers of red and blue here, the red group is just like way underrepresented in the outreach as well. So they don't hear the information as much as the blue group. If you do impose this parity constraint at the level of the outreach, maybe the information reaches people in a more proportional way, but you're going to reach fewer people in general. And that's what they show. And our work came out kind of at the same time with a slightly different approach. Is there a question? Yes. Here.
So how bad can this be? Could it, for example, be that, let's say I look at the optimal fair seeding, I get sort of, as you're an example, 2 red women and two red and 2 blue, because it's 50-50. But now you do your optimal. What if in the optimal you suddenly get 3 red and 20 blue? Maybe then you don't care because you say you actually, while you might not be as fair, the minority is better off if I do the, so. Yeah. So this might not be quite the right measure because I might, you see what I'm saying? Do I care about fairness? Am I unhappy because my neighbor is rich, or do I just want to get as many red people rich as possible?
Well, you would, I see your point. I think the actual metric that they use is to say like, if they use this together with another one that says like, if I have like 50-50 red and blue, and if this, in this case, I reach only, let's say like 2 out of 10 people who are red. But in this case, sorry, let me find what the right example for that. I think the idea would be that you're measuring the proportion of people who are red who have reached, the fraction of people who have heard this information in both cases, and you want it to be more or less proportional. So you can have both definitions, that one and one that says, in the case that you mentioned, I actually reach more people in general in red, so I have 3 as opposed to 2. So I'm actually increasing the rate at which I'm reaching red people, which makes it in a sense more fair. But if I reach 1 red person and 9 blue people, then I'm less fair. And that's the case that they kind of observe.
So that's what they found. So they didn't find this strange behavior that you
Not
could
really.
make the reds better off, but it's less fair.
Yeah, I don't think they have found that, because in a lot of the cases they found that you actually reach a smaller proportion of the red community in general as well. And I think of course it depends on the network, but we'll discuss assumptions where that might hold or that may not hold. So with that in mind, our approach was to think about how do you recover this gap between information access between the two groups in the following way. Think about that we have partially known networks in which we may be able to use centrality metrics such as degree, or distance centrality, or local information that we may have. And we're going to use a model of network growth in trying to tap into the inactive communities, those that have been left out in a way that's trying to recover that lost gap there. And with that, we're actually able to prove that there are theoretical conditions, depending on the network model and on the diffusion process, for when being more fair can actually increase your efficiency overall. And the intuition is that, well, you kind of left out the whole group of your population out of the information loop when you just focus on very central people. And I know this idea has been floated around earlier, but this is what we're going to discuss in detail today and what theory can tell us about this problem. So this problem was very much inspired by the talk that was earlier today, just a few seats more. If you saw it, the main takeaway was that you can do random seeding with just a few extra nodes, and you're going to do you're going to do comparable and sometimes better to optimal seeding. So in case in which you don't have network information, you might as well be random. And if you're able to have some flexibility on the budget, then you're able to be pretty comparable to how well an optimal seeding would do in terms of the outreach. And then our thoughts were, well, that would be great to do so, but what if we are able to leverage that in a strategic way to make sure that different communities reach, they're being reached by the information in a more fair way or more diverse way. So the main vision was that the bias that you see in this information gap is a sign of inefficient seeding. And by tapping into these inactive communities, we're trying to do that in the early adopter set rather than in the outreach and earlier in the pipeline, and see where that leads us, and seeing that we can do that with a knowledge of a network model and thinking about different centrality metrics. This is a way to figure out what's the effect on the outreach and hopefully get a better outreach in particular conditions. So if we're thinking about awareness of labels, how we might try to implement this kind of constraints in different centrality metrics. For example, if I'm looking at the degree distribution, I can think about doing, I can impose statistical parity in the campaign in a way that's strict. So I want to ensure that the proportion of people in the early adopters among the two communities is almost the same or exactly the same as the general population. So it's a strict condition. Or I can do the same thing, but in a relaxed version where I allow some epsilon wiggle room that actually in practice helps so much with getting more people in the outreach. And I want to compare how this strategic seeding, in which I'm trying to impose this kind of constraints, will compare with the baseline in which I don't know any community information. I only know the network, and I'm seeding based on my usual centrality metric, for example, degree. There's a question in the back.
Since you know knowledge of the network, why impose the statistical parity on the seeding as opposed to estimate the outreach for the seed and enforce the parity on the outreach?
Yeah.
Can you repeat your
I'll repeat the question. So if we know the information about the network, why impose the constraint at the level of the early adopters instead of the outreach? So earlier, there's the other paper that's related to this, which is this one, is showing that if you do impose this constraint at the level of the outreach, in most cases or not, you're going to get this trade-off, and this trade-off looks quite big. And it looks like if you do that, our intuition was that you're not actually being efficient in the seeding when you're imposing this constraint in the outreach. But if you do impose this constraint at the level of the early adopter set, then you're able to actually improve the seeding in a way that's leveraging network information in a better way. This one doesn't really leverage network information that much in a way, or it is, but only at the level of the outreach. So I think it's interesting. I don't know if there's a particular proof or something rigorous that we can see with that, but that's a big difference. You get a trade-off here, you don't. There are many cases in which you don't get a trade-off where you impose this constraint earlier. And the rest of the talk, I'm gonna show you how imposing that constraint earlier is gonna help out a lot. Other questions at this point? Yes.
Just to come back to that question, so I guess the idea is that you're not fair because you select anyone who doesn't have the same degree, for instance. So the distribution of the degrees is different. So if you do parity on the seeding, actually to come back to your going to guarantee parity in the outcome, because eventually the assumption was that there was a shift in distribution, right?
Yes. So we're going to see that. That's basically, let me repeat that question to, I think, for some people to hear also. The question was, if you impose a constraint at the level of the early adopter set, how do you guarantee parity in the outreach as well? And you can guarantee it in very particular conditions. So depending on how the network actually looks like, you can guarantee it. And depending on the network structure, you may be able to impose slightly different constraints on the early adopters in order to guarantee parity in the outreach. And I'm going to talk about that in the network model to show you like when you can guarantee and when can basically probably cannot. Great, but these are good questions. So then let me show you how this would look like as an example of what does it mean to impose this kind of constraints on a centrality metric. For example, let's say we're looking at degree. Degree sometimes does well, sometimes it doesn't really do that well. But in a lot of the experimental data, it's something to start with. If you're choosing a seed set based just on degree and you have a particular budget, you're just gonna look at that budget and choose people above a certain threshold, no matter what community there are. This is just them ranked by degree, and that's your early adopter set. If you want to be fair in your early adopter set, if you want to be strictly fair, you're gonna say, well, how many people who are red and who are blue do I have in my general population, and how do I get them to be in that early adopter set? So I have to choose, in this case, as Claire said, maybe you have different degree distributions, which is one mechanism through which a degree centrality will be biased or will be unequal among the two communities. And in that case, you'd say, well, I do need more of the people who are red. I do need to lower my degree threshold for them and include those with a bit lower degree, but I do have the budget, so I need to choose fewer of the blue people before. So that means I chose people who are in the minority, or in this case, not minority, but who have lower degree, and I added them to the seed set. And I want to know what happens now with the outreach. And I can do that in a way that's strict, or I can do that in a way that's in a relaxed version in which maybe I don't need full statistical parity. Maybe I can have some wiggle room up to some epsilon. Okay, so I want to show you like this kind of strategies work with particular depending on the assumptions that you have with the network model itself. And one of the reasons we're using that is not to say like this is the right strategy necessarily to use. This is just one methodology that depending on the network structure, you can differ your strategy on how you choose people in the seed set, depending on what you can estimate from the network itself. And the network model that we're using is basically serving the purpose of trying to explain where did bias come from. We know there's some bias in the outreach. That's something experimental data has shown in the past. We also noticed that, but we want to know like what's a mechanism that would tell me this is why degree centrality is biased, or this is one way in which some centrality metrics are biased. So in a sense, it explains one model of degree difference or distribution in degrees difference between the two communities and how that may propagate within the seeding algorithms that we have. And it's useful to prove our guarantees about what we want to know. And basically it tells us, it's one mechanism to tell us like where and how we should intervene based on that model with these strategies to improve seeding. So let me tell you what a model looks like. And based on a model, you're going to see that, well, it will be quite intuitive why some assumptions in this model make it easy to be more fair, but it don't depend necessarily on the model. It's just that depending on what assumptions you make, you may be able to create strategies that are more fair. So the model that we're using is a variant of the preferential attachment model in which you also have two communities. So you have two groups. Someone comes into the network, they choose a label, blue or red. And let's say these two groups are different in numbers. So let's say the fraction of the red nodes is smaller than half, they're in the minority. At each time step, new people come in, they choose their label, and they create a number of connections by connecting with probability proportional to the existing node's degree. Once they do that, though, there's a third element to it, which is homophily. That's an assumption in this model, meaning that if you have different labels, you're going to connect only with the probability row. And if you're the same label, you always connect. So if you don't connect, sometimes you may rewire. And this model was proposed a few years ago. It's really interesting because it has this skew degree distribution that sometimes it's interesting to look at. And it has this community effect. And it's really easy to really useful to analyze in terms of centrality metrics. So let me show you an example of how this model looks like. You have a snapshot of the network at a particular time with connections and nodes. A new node comes in, it chooses a color, blue or red. Let's say it's blue, and it connects with preferential attachment. Let's say it chooses this node. It's a different color. So because we have this rewiring probability that is motivated by homophily, it would say it will accept or reject the connection. If it accepts, it will accept it with the probability of homophily row. If it rejects, it just redoes this process until it gets an edge. And you can do that by everyone creating a number of edges with the existing network. And this model grows asymptotically. So the purpose is to analyze what happens with seeding strategies, giving this model asymptotically as well. The model is interesting in the sense that it shows there's an inequality in the degree distribution between the two communities. And Avingen et al. Show that, well, we know that preferential attachment follows a power law. This model in the two communities also follow a power law, each of them with a different coefficient. The fact that this coefficient is different is one way to think that that's one case in which you're going to see degree centrality to be biased, of course, because the proportion of nodes in minority is going to be over a certain degree, or it's going to be basically vanishing as the degree increases because of this power law difference in the coefficients. So if you're back to our seeding strategies and trying to compare them, this is one way in which we see what we see in the data, basically that a lot of the centrality metrics, including the degree, what I'm showing here, shows that one of the group is really, really underrepresented. They have much lower degree than everyone else. So the purpose is to compare these strategies and to figure out like when they can do better, both in terms of fairness, but also in terms of outreach. And the first result, which is intuitive given the assumptions of the model, is that, well, both diversity seeding and parity seeding can lead to a fair outreach for the same budget. So they can improve the proportion of the minority that's being represented in the outreach, given that we have the same constraints. Why? Because, well, the network is homophilic. So if you add more nodes, even if they have lower degree in the seed set, they're just going to reach more of the community that they're a part of. That wouldn't work, of course, if the model is not homophilic. And depending on that, you may want to change the strategy in what kind of thresholds you may choose for this, or who are you actually including in the seed set selection. But in this particular case, in which we're assuming homophily and this kind of strategies, this is what you get. The second result that's less intuitive than the first is that there is a particular point, there are a set of conditions in which both diversity seeding and parity seeding can outperform agnostic seeding in the outreach. They do better. And that point depends on the size of the seed set, how big your budget is. For a very small budget, I'm going to show you how that looks like. Maybe you get a trade-off. In practice, the trade-off is actually really small. And at some point, as the seed set size increases, you're able to be more fair and more efficient at the same time. Question? Yeah. Yes, sorry, this is a typo. Should be, the constraint is that the seed sets are the same size for all three seeding mechanisms. Yeah, thank you.
She wants to make sure you're paying.
That was the test. Okay.
Anyway, it's true what you write there as well. So.
It is true. A main intuition of the proof is that, well, the goal is to basically figure out whether there are these thresholds, basically these different thresholds that we can choose in order to get a better outreach, or to be able to estimate an outreach that's better in parity and seeding and diversity seeding than we would have with agnostic seeding. And it's not necessarily easy, but it is one way, because of this model, it is nice to be able to compute it in a couple of steps. First of all, by estimating the first step influence size of a particular seed set, and then extend that to an estimation by multiple steps of the size of the cascade given a particular seed set for a particular threshold. Given that you have a budget that you may care about here, here, should be a budget, you can compute what's the degree threshold that you need in order to get that many people in the seed set size that you have. So if I have K people in my seed set size, and I'm choosing them by degree, I know how many people I need, what's the degree threshold above which I can choose, because I know the degree distribution of this network. And I know it for both groups, but because of that, I can compute it in general. I'm not going to talk about the second step, which is an estimation step, but a quick point about the first step in doing so is that we do know the size, as I mentioned before, we know the degree distribution. If I was a power law with different coefficients, so we can estimate a variety of things, including what would be the degree threshold above which we need to choose nodes in order to be within our constraint. And we can compute the first order influence by computing basically the probability of a node being influenced by one edge, whether it's a blue and red, and combining these two to have our estimation. Once we do that, which basically all of this rely on the network process formation, because I can write this in terms of like what's the probability of an edge to have been formed versus the fraction of edges that have been formed among different communities, and I can estimate this. Once we do that, we want to go back to thinking about like, well, can I have these two thresholds that give me an expectation of better outreach if I have different thresholds or not? And one way to do that is a mechanism in which I just think, well, I can just transform this into a function of figuring out at which point in these different thresholds do I have to be in order to get a better outreach, and writing that as a function of that point in X in a continuous form, I can just study the analyze the behavior of that function and just basically figure out that that point exists, and you can compute it in closed form and find a particular threshold above which the seed set size is large enough so I can be more fair and more efficient at the same time. But I want to show you how that looks like. So the way that would look like in theory, and I'm going to show you how that matches to the data soon as well. This is basically theoretical simulations from a network generated from this preferential attachment with two communities. And the parameters fit more or less the data that we have used as well. So if you have, we have about 53,000 nodes, two communities, some homophily parameter. And on the X axis is the size of the minority. So at 0.10, you have 10% minority in red, 90% majority in blue. As you move towards the right, you get to more and more equal subpopulations, where you get at the very end 0.45 means 45% are minority in red, 55% majority in blue. The y-axis is the seed set size, the size of our campaign. And here we're looking at pretty large campaigns. I'm going to show you a few experimental results on smaller campaigns as well soon. The different colors represent on which heuristic did better in outreach compared to the agnostic. So if you look at the orange region, this is the region of parameters in which being agnostic will get you better outreach than being diverse or for diversity seeding or parity seeding. It's basically telling you you're going to get some trade-off between being fair and being efficient. And that trade-off is not really large, particularly in practice, but it's there. As you move up on the y-axis, at some point you reach a size of the campaign in which you're transitioning into this blue region. And this blue region tells you that you're going to do better in outreach with diversity seeding than agnostic. And as a side note, well, diversity seeding is a relaxed version of parity seeding, so it's always doing better than the strict conditional statistical parity in outreach. And what you notice here is that as communities become more and more equal, so we're moving right on the x-axis, you get this blue boundary line that's monotonically decreasing, meaning that you need fewer and fewer seeds in order to be both fair and efficient at the same time. And in a sense, with this relaxed version, that makes sense because the communities are more equal. You're not, when you're choosing nodes with lower degree, you're not actually like losing so much in your influence potential. But a different effect happens when we're moving up on the seed set size parameter and we enter in this purple region in which actually when you have enough seeds, the strict parity condition, parity seeding also performs better than agnostic in the outreach. And that's where being strictly fair also gets you to be more efficient in the outreach as well. And what you notice here is that, well, as the network becomes more equal among the two communities, at some point it becomes really much harder to be more fair and more efficient at the same time. You need much more seeds than you had needed before. So it's no longer a linear effect, which at the first glance, it's a bit contradicting or not expected. But when you think about it, basically when you have a small minority, if you're trying to be strictly fair, you would say, I want a node from my minority group, and that node is going to have much lower degree, but that's okay because it reaches a community that I have not influenced before. I would have not chosen that node in my agnostic seeding, and now I reach a new community. But when the network becomes much more equal, these minority nodes don't have such a low degree. They're already pretty high degree. They've already been influenced. The minority community, it's not a new community I'm trying to tap into. They're kind of influenced, but it's really much harder to get them to be influenced in a fair way. So in a sense, that's why I need to spend way more budget to use this lower degree nodes in order to be strictly fair. Whereas in the other case, when I'm choosing nodes that are very central, that come from a majority group, I'm actually being inefficient because I'm choosing nodes that have this overlapping sphere of influence more or less. Although they have high centrality, they're not really getting me to new parts of the network.
So Anna, I have a question.
Yes.
So you say this is a theoretical analysis, but it's a simulation of your model, right?
So
can you actually do this also analytically or not? Because preferential attachment, I mean, percolation, so you eventually have to do percolation on preferential attachment. And now you have to do percolation on preferential attachment with these two types and stuff.
Yeah.
That sounds pretty scary to me.
It is. But what you can do though, is that this previous result is telling us, where is it? Here. You can do some estimation of the influence, perhaps for a few steps, and then from then on assume that that's as much as you can go in this estimation with the preferential attachment. And it's basically telling you that we can find this closed form threshold such that we know when we can be more fair and more efficient at the same time. We know we're always going to be more fair. That's something that's easier to prove, but it's harder to prove when we're going to be more efficient too. But basically this is telling you that, yes, I can actually know the form of this parameter. So at any particular parameter, I know where this threshold is. The theorem tells me like what a threshold is in theory, and then I take that and I compute it and I plot it here. So this is not simulated from when is the outreach actually better in simulating influence. This is simulated from the theory result that is telling us where this boundary line is. Was that a question? Yeah.
Right now I don't. So is this curve? So this is a numerical. So is it simulated like Monte Carlo, or is it a numerical solution of some equation?
It's a numerical solution.
Of some equation with some differential equation
of
for
some
these curves
equation
also.
That we saw before. Yeah.
Okay, thanks.
Yeah.
You have a question also in that call.
Yes, a question there.
Can you say something about how much one strategy outperforms another in these different regions?
Yeah, so in theory, we can't really estimate by how much. Like these three results are kind of limited to showing it will outperform. By how much or a bound on that, we don't have. That's an interesting thing. I hope someone works on that. Yeah.
And simulations?
In simulations, you can definitely do it. So I'll show you what happens in simulations that we're simulating the cascade, but on real network data. So let me show you how bad or good this gets, given that we have a real network data that's collected from DBLP, this network of computer scientists, science papers, where there's a citation network and there's two groups, men and women. And the women are in minority in this case. They're about 90% of the population. So we're about at this vertical line here. So what we do here is you can simulate the diffusion process average it over many times, and report what happens at different level of the seed sets.
Did you observe homophily this time?
Yes. So this simulation here is based on an estimated homophily parameter from the data set itself, which tells me that there are two homophily groups. And these two groups, yeah, they're quite clustered together, basically. And it's something similar we saw with a bunch of other data sets in which homophily was available as well, but I'm only showing one. Okay, so let me show you what happens. Let's say you have like a relatively small seed set size, not that small, but you have 1,000 seeds given the network size. We're basically, the theory tells us we're in this region or where agnostic seeding should do better than everyone else. And it does so, not by much. This is averaged over about 10,000 simulations. So what you see in the first row is that both parity seeding and diversity seeding, they lose some outreach, but they lose so little outreach. Whereas they do improve the fraction of women in the outreach as well. If you do increase the number of seeds, what happens is that in theory, let's say we're looking at 5,000 seeds, theory becomes a little bit more conservative than what the real data actually shows, in the sense that we're expecting to still be in this agnostic does the best case in this orange region. But in practice at 5,000 seeds, we actually moved in the blue region where diversity seeding actually starts to outperform agnostic seeding in the outreach itself. And this is for one probability of diffusion 0.01. It doesn't outperform by much. Again, the difference is pretty small. But when you think that you remove some high degree nodes and you got some lower degree nodes from the minority group, and they were able to overcome that difference and influence overall more people, that's where you see this difference looks more exciting. Question?
Is it a random network? Like if I cite someone, random or not random, like what are the expressions?
Yes. In this case, we work with, let me remember, I believe it was unoriented, if I remember correct, but I will check.
So you remove the directions.
The analysis of the model can be done for both oriented or unoriented. You get a similar result of the degree, but I think I'll check that. I don't want to say something wrong. So so that one happens for 5,000 seeds. Let's say you're increasing the number of seeds, and at some point, let's say we're looking at a bit above 9,000 seeds, and you're expecting, again, the theory actually shows to be a little bit more conservative of what the simulation shows, because in reality, what we see is that both parity and diversity actually get you more people in the outreach overall on average. So in practice, we're actually in this purple region that the theory suggested. So here what's nice to see is that, well, depending on how big your seed set size is, you may want to do different things. You may have a trade-off between how many people you're reaching and how was the fraction of different communities in the outreach as well. Both with this data set and with other data sets we looked at, the difference is the trade-offs are really, really not that high. The nice part about showing or having this constraint at the level of the early adopters is that it allows us through the network model to estimate the cascade and to get us this map that more or less in a conservative way matches to what we see in practice too. So it would tell you like that it is worth doing or trying to explore the network a little bit more. And of course, the methods that you may use or the exact thresholds you may use may depend on the network model choices that you may have, because this is all based on having, of course, you have a homophilic network and you add more people from one of the group in the seed set. Of course, you're going to get more of those in the outreach as well. That may differ if the network looks different as well. There are different extensions that we were thinking about, including like, what happens for different mechanisms, seeding mechanism instead of like degree. So for example, if we're looking, let's ignore that, well, I'll talk about that extension. But if you look at degree discount, a very similar effect happens. If you're looking at fewer seeds, so like if you're looking at very small seeding up to like, I don't know if you can see the numbers here as I see. Anyway, up to 30 seeds, the plots here just show you the outreach between the different seeding mechanisms. Let's say you have agnostic or diversity and so on. They're pretty similar. The trade-off is really, really invisible almost over many simulations. you can do more than that and think about, well, I can be fair at the level of my seedset selection. I can be fair at the level of the outreach. Is it worth thinking about interventions in between? Does more network information or an intermediate network information level actually helps me? And it does help me. Like, for example, if I think about extending the statistical parity condition from the seed set to the neighbors of the seeds and thinking about what's the community affiliation of those, call that neighbor seeding, that actually helps quite a bit. It helps in the degree. And again, maybe the other screens are better for these pictures. But what I'm trying to show is that the outreach is very, very similar between agnostic seeding, diversity seeding, and neighbor seeding. And actually, you do get a higher fraction of the minority in the outreach for neighbor seeding than you would even for diversity seeding itself. There's no theory that we're proving for that. This is just experimental results. And if you do increase the number of seeds to say 1,000, neighbor seeding does actually pretty well in practice too. So depending, of course, on like how well the centrality metric does as well. You may think about, well, what happens with greedy? Maybe degree is just like a terrible thing to do if you actually might want to do greedy instead and you have enough network information. Well, if you do look at greedy, I'm just showing here for 1,000 seeds, but a similar effect happens for a larger amount of seeds, is that the trade-offs are really small. Maybe neighbor seeding doesn't do as well, but diversity seeding actually does really, really well for a variety of seeds. Here's just 0 to 30 seeds, a very small seed set selection where the outreach are very, very similar, indistinguishable. If you do increase the number of seeds, 1,000 or even above, you actually do better in diversity seeding. Here's a question. Sorry? So the greedy algorithm is the same algorithm from Kempek, Kleinberg, Tardosh, where you do it iteratively, you do get a no, you get the first no with the best influence maximization over many rounds, and then you choose that one and you get the next one that gets you the best marginal increase in influence than what you already got. So it's trying to use this submodular property of the independent cascade to get you to a good algorithm. It's much harder to analyze greedy theoretically, so that's why we looked at mostly network centrality measures for which you have just partial network information. With greedy, you would assume you have the entire network information. And a bunch of very similar results happen for a variety of other metrics in practice, from like degree discount, which is a version of greedy in which you're trying to discount where nodes of high degree have similar spheres of influence and to like remove that, or for between a centrality and so on. And even for random, but at that point, random is just a very fair heuristic. And if you want to use random, it should just be random, and that's probably fair anyway. So there's a bunch of directions from here and a bunch of open questions, some of them that we have mentioned before. What happens with other models beyond independent cascade? A related work was studying fairness in the linear threshold model. It becomes much harder to prove, as people have previously mentioned that as well. What happens for other centrality metrics more than the practical solutions we see? That's another question. What happens for different kind of models? Our model is pretty specific. It looks like how the data looks like, of course, but you may be interested in other modeling choices depending on what data you have. And other questions such as, how does the network formation process take place with relationship to who influences who? There are recent works that are working on this from, for example, this paper on causal estimation of peer influence in social networks. Am I friends with people because we influenced each other, or did I influence them because we were friends to begin with? So that may inspire different kind of modeling questions to study. But I think I'll stop here and let's see if there are any other questions from everyone.
Let's see if there are questions. Yeah.
So the paper that you had 3 colors and you did like medial. You said there was
If it, is it on? It's better. It's on. Okay.
Yeah. So there was a difference between theory result and the experiments here. Did you try to like change the homophily, like to see if qualitatively like these curves look the same, like this convex and the concave curves?
Yeah, no, we did. So they do look similar in shape when you change homophily. There just depends, like the threshold actually changes because it is an input to the parameter, to the threshold that tells you how many seeds you need. The homophily parameter we use here, we try to estimate it from like how the data looks like, but maybe there might be a question like maybe that's not the right estimation, or maybe there are better estimations for which we can get slightly different figure of where exactly we are in this space, but the behavior is the same. Yeah.
And why do you think is the main reason that you see this?
Our intuition was that, well, on the one hand, if you have people who are very central, if you have a very small minority and you're in this region, you would expect that basically the people who have very high degree have this overlapping sphere of influence. I have a small minority. If I'm choosing someone with small degree, I'm actually getting to a new part of the network. So I'm gaining a lot. So like as the network is like relatively, as the minority is relatively small, I'm kind of following the same trend as diversity seeding. But at some point, the minority group is large enough that in the degree selection or in the degree centrality, they're still kind of represented. They're not completely out of the loop. They've been influenced to some extent, but it's much harder to influence them to the actual proportion that they have in the network. And there's this interesting, basically competition that happens when nodes of minority community come into the network and you have homophily. They kind of try to decide like, well, am I going to connect with a majority node that has a higher degree, but it's a different color, or with a minority node that's the same color as me, but lower degree, which creates this community effect. And when you have that, and you still have a relatively large minority community, is like they have lower degree, but they're still kind of influenced. So it's really hard to overcome that. And you need much higher seeds to seed set to overcome that. That's our intuition from it, but yeah.
Oh, and a little bit tangential, but like it seems like at least in the simulations, the fairness of the agnostic seeding seems to be not that bad, right?
Yeah, depending on how many seeds you get, it can be terrible or it's not that
yeah
bad.
So is it monotonically, like I wanted to know whether if more seeds are making my fairness better, like in the sense is, can I say something like I only need a few more seeds to become fair, like even if I do like agnostic seeding, can I get something like that result? Like
oh, I see what you mean.
like I don't know anything about the network structure. All I want to say is that instead of using 1,000, if I can use like 2,000, okay, that's a big jump, but like if I can use 2,000, can I get a much fairer? Am I getting close to being more fair, or is it like very wacky, like that there is no
Not
such?
really. It doesn't really change with the seed set size. I'm only showing like 3 iterations of seed set size, and this is for this data set. It doesn't do terribly. So I have 19% of women in the almost 90% in the data set. Maybe this is like 16%. So I lost 2%. Maybe it's not that terrible. In other data sets, the loss is like much higher. But even in this data set where the loss is not that bad, and those as well, I can go as low or as high, and I'm not actually like improving. It's the same. It's going to stay the same at whatever seed set size I have. It's in practice, it doesn't help that much.
Thank you.
I mean, maybe sometimes it helps, and given maybe it would help if instead of agnostic seeding with that set, as the previous results show, you would do random seeding, and in random seeding you do get a similar outreach, but you're expected to be much fairer.
Thank you.
Another question? Yeah.
Hi. So I have more of a general, like, kind of intuition question. I guess I was wondering, so here you have a constant homophily parameter, right? If you were assuming kind of, say you have two classes of homophily parameter, where one is, one's minority group is much more likely to connect to their homophilous, and another one is much more likely to connect to. I wonder if, like, I guess intuitively, I might think this diversity outperforming in the purple regions will kind of shrink as you have larger gaps in
Yeah.
Like, what's your?
I think your intuition is right. We didn't do that analysis. We did do this analysis for this model with a different application in which you can set different homophily parameters. And basically you can compute everything in the same way. So it doesn't really add much complexity, but you're able to see differences. One thing that you do notice is that we did notice is that when you do have a minority that has a higher homophily parameter than the majority, actually at some point, the degree distribution gets to be the same. So a more homophilic minority is able to actually get you the same coefficient in the degree distribution than as the majority in some conditions, depending on like how close together, like what the homophilic parameters actually are, and on the size of the minority. If you have like 1% minority, no matter how homophilic they are, they'll never be able to equalize this. But if they're in some ranges that you can actually prove for this model, you can show that these actually like become equal. And when those become equal, maybe it's not such a big issue to think about seeding or how to make seeding fair, because it's already kind of fair because their proportions in in centrality metrics are the same among the two groups. But I think that's a really good question.
Quick follow-up. Do you when you're looking at this DBLP data, do you actually notice that a constant homophily is a better estimate of the data, or is there a distribution there?
Good question for that. It wasn't that different from what I remember in the data, and other data sets becomes really different and it creates interesting effects. This one is more or less the same. Definitely, I think the minority in this case, the women were a little bit more homophilic, but not by much. But I can look up the table for that later. Yeah.
I have one question about the type of analysis, type of proof that you have here. So you can do, you look at a branching process starting from a random node, and you can follow based on the homophily, measure how many vertices you see from each time.
Yes, you can do
That's
that.
the part that Christian was saying is like becomes complicated.
It becomes really complicated after a sample. You can do up to like a few steps, and you can do up the first step. It's easy. Second step, you can still do it. Third step, you can kind of do it, but it becomes really complicated. After that, you kind of approximate it, and then it's not a very clean result to approximate it beyond that. So that's as much as this gets us.
I see. I was under the impression that your branching process, you have to worry about only the first step. After that, as long as it's tree-like, it will be the same. So you're saying it changes in generation?
Oh, I don't know whether it actually changes after a couple of steps. Like it becomes, in a different analysis, we're looking at like random walks of length 2 on this in this graph, and looking at how random walks of length 2 compared to your immediate neighborhood, and they're not that different. So I don't expect that it actually changes that much between 1 step, 2 steps. It's kind of the same. 3 steps. It becomes kind of hard to know how similar it is because the equations get really complicated. But beyond that, maybe it does.
All right. If there are no more questions, let's